It is my pleasure to introduce the next session keynote speaker. It is Professor Fumihito Arai from Nagai University. He is a very distinguished researcher in our community. He earned the Early Career Award from our society. He also obtained another 55 additional awards for his research. He published over 300 papers and holds almost 30 patents. So I think with that, to not take too much from your time, we're looking forward to your presentation. Thank you very much.
Thank you very much for kind introduction. My name is Fumihito Arai from Nagoya University. Today, my title is a little bit large, Micro-Nano Robotics for Biomedical Innovation. However, I have only less than 20 minutes, so I'd like to focus on a recent progress on-chip robotics in our laboratory. We are studying about this topic almost 15 years. Okay, so this is the outline of my talk. So first, of course, this is IROS. So robotics is very important also in biomedical field. And we are thinking about integration of microfluidic chip and robot. Robot is put inside, and we call it on-chip robotics. So to realize such kind of a delicate technology, we think micro-nano fabrication is quite important, very important. So I'd like to introduce some key points how to realize on-chip robotics. And of course, floating cell control is quite difficult. So I think we'd like to discuss how we solve this problem. Okay, so let me start from the introduction of lab-on-a-chip. This is quite a simple on a chip. There are a small microfluidic channel, and there are lots of good point advantage. The energy saving, size is small, and low environmental load. Therefore, it can be applied several applications like gene analysis, early diagnosis, preventive medicine, or POCT, or something like that. So thinking about works on a microscope, we roughly classify into measurement and manipulation. In measurement, there are lots of topics like environment control and cell measurement. Like in this talk, I'd like to focus on stiffness or impedance measure of single cell. And to do that, we need some manipulation technology. So conventional way, such a microfluidic chip technology is very popular. But the function is quite limited. It can only manipulate a liquid reagent. However, sometimes we need physical interaction. For example, separation, cutting, or applying force to measure the stiffness of the cell, or sometimes vibration or dispensing. So thinking of this kind of functions, we need a robot, but the size is quite different. So we conclude to miniaturize robot part, and that can be integrated in the microfluidic chip like this. The key issue is how we control such a small object in a microfluidic chip. So basically, we are thinking about non-contact manipulation, because to do that, we can make the chip disposable, right? So we have studied about non-contact actuation method using optical tweezers or magnetic force or electrostatic force. However, thinking about a variety of manipulation, magnetic force is quite useful for us. So we have developed a lot of families. For example, sorter here and mixer here. There is a magnetic rotor inside. And this is a loader in high speed. These small particles are loaded one by one, like machine gun, right? And this is a rotation by the induced flow by vibration, and multiple degrees of freedom, and cutting, right? This is the elimination of nucleus of oocyte. So the motion is quite elegant. And however, the accuracy is quite big issue. So we made a small group, we call it rivulet. Then the motion as a higher frequency is greatly improved up to 10 times. So in this case, the frequency response of the system is around 90 hertz. So this value is relatively very fast in this area, in this field. And the output force is very large. It can output around a millinewton order force. I think millinewton order force is enough for such a biomedical application. Okay. So using such kind of high-speed manipulation, we can vibrate the tip of the micro tool like this. Then flow is induced around the tip of the manipulator. Then you can see these small particles are used for visualization of flow. Then when we put the oocyte here, it can be rotated like this. When the tip is stopped, then the rotation suddenly stops, right? So such kind of application in a highly viscous, low Reynolds number environment is quite effective. But today, I'd like to introduce application of on-chip robotics for active sensing of single cell. For example, viscoelasticity of the cell. In such kind of application, robotics plays an important role. So motivation is here. Currently, single cell analysis is quite popular. So you can see that this is an adherent cell. Can you see which one is a cancer cell? I think nobody can tell which one is a cancer cell. The answer is here. These two are cancer cells. So from the image, it is almost impossible to measure tell which one is a difference of the cell. Of course, we can use fluorescent dye and fluorescent microscope. Of course, there are another technology to visualize them. But, well, of course, we'd like to know much more different properties like a chemical property or physical property or sometimes proteomics. So thinking about this, I think single cell analysis is a very important research topic in future. And for measuring the mechanical stiffness of the cell, so normal and popular method is using atomic force microscope, AFM. Professor Okajima at Hokkaido University is using AFM, and they can visualize stiffness mapping like here, each cell, elasticity or viscosity of cell. So the brightness means difference of the value. So this is a very important technology and very effective method to visualize the mechanical property of the cell. However, how about measuring floating cell? Of course, they are floating in the water or liquid. Therefore, AFM is quite difficult to measure the mechanical property one by one because they are floating, right? So thinking about such kind of application, we are thinking about on-chip robotics. And this is a magnified view of the probe part. And the cells are flowing one by one in high speed. And this probe is moving like this by controlling the outer magnetic field, then apply force and deforms the cell and measure the force, right? This is a simple concept. And to do that, we need high accuracy, position accuracy, less than 1 micrometer. So we employed such kind of mechanism to decrease the displacement. Then this is the side view. This is the on-chip probe, and we put a permanent magnet beneath the microfluidic chip. Then this probe is moving like this. Then we can measure move the probe, and this is the force sensor part, and we measure the mechanical property like this. And speed is very fast. Let's say around 100 hertz, like this. And by using such kind of probe system, we can measure the mechanical property of the cell. So this is time, and this is cellular force, and this is a theoretical value, and this is a measured value. Then based on this experiment, we can estimate unknown value like this. This is a very simple experiment. And this experiment was done for the oocyte. The size is 100 micrometer. It is relatively large. And however, in the case of animal cell around this, so the size is much smaller than the oocyte, around 10 to 20 micrometer. Therefore, quantitative evaluation is quite difficult because target size is small and they are floating, and the power needs more than nanonewton order, and the resolution is much more higher nanometer order, and we also need a high throughput. So this is quite challenging. So first we try to apply the same device which is used for the oocyte to the animal cell. However, the probe thickness is very large compared with the size of the cell. Therefore, when we apply the magnetic force, the tip probe is fragile, so it's broken. So it is very difficult. Therefore, we try to use a silicon on insulator, SOI wafer, and this only probe part is thin, right? And this pushing bar is very thick. And we apply force using outer actuator, then deform like this, right? This concept works well. However, there are a lot of problems. So anyway, I'd like to show you the concept first. We call it direct outer drive mechanism because we need a very high precision, nanometer order. So we use a piezo device, PZT stage, which has a very good accuracy, right? And this is moving, and this probe is pushed, and this bar is moving, yeah, like this. So this is a simple concept. So issues on microfluidic chip for manipulation. So we used to use PDMS. So this is a polymer material, and glass is bonded together. However, it is a soft material. PDMS part is quite soft, so accuracy is quite low. And robot part, this is made of polymer magnetic particle or photoresist. This is very bad material for on-chip robotics. And the silicon and magnet. These are not good because of low accuracy. This is not suitable for cell manipulation. Therefore, we concluded to change the material completely. For measurement, we don't use PDMS. We use silicon on insulator, SOI wafer, and glass, right? Then, this is a Young's modulus. It's very stiff, so that we can realize stiff and accurate rigidity is more than 60,000 times higher in the material base, right? And robot part is made of silicon insulator, and this is driven by outer piezo driver, the direct and precise. Therefore, we can realize high accuracy and high speed. But fabrication is quite difficult. This is a final chip, but we need a lot of delicate micro-nano fabrication. And this is deep RI etching, and the bonding. Bonding is very difficult, but rigidity of material is very high. So final product is quite rigid. So we can expect good accuracy. So packaging is a very important issue for on-chip robotics. So in a case of using PDMS glass, PDMS is very soft. It's only 1 megapascal, and the bonding is quite popular, and the bonding is easy. However, glass silicon bonding, it's quite difficult. Like this, there are lots of different ways like anodic bonding, plasma CT bonding, AU diffusion bonding or something like that. And this is good used for rigid and stable material like glass and silicon. But this bonding technology is under development, and bonding is quite difficult. So firstly, we focused on anodic bonding and currently plasma-assisted bonding. And we took almost 3 years to complete this technology. Anyway, so this is a brief introduction of anodic bonding and improvement. So first, glass, Tempax, and silicon is prepared, and we prepare electrode and apply pressure, assembled, then apply heat more over 400 degree and apply voltage around 500 volt. Then we need a high voltage and heating and pressure on silicon wafer to contact both surfaces firmly. However, it is not good because it can be broken, right? So should be decreased to protect the chip. Therefore, we are thinking about the surface state treatment. We need a clean and active surface for bonding. So first choice will be the forming intermediate aluminum layer or something, but this is opaque and not transparent, so not suitable for cell manipulation. Therefore, we are using cleaning surface by plasma bombardment first, then sequential plasma assisting using O2 plasma and N plasma like this. Then finally, we succeeded in bonding of silicon and glass successfully. Then the probe, the tube is connected horizontally. Then we can flow the cell seamlessly, right? So this is a example of driving on-chip probe like this. It moves like this. And of course, it is driven by PZT stage. So frequency is very fast. And the position accuracy is very good. However, there is another issue because bonding is so successful, but we have another issue of residual stress by assembly, of course, direct bonding between. Therefore, when there is some residual stress, so this is a force sensor bar, and there might be the residual stress here. Therefore, we change the design of the force sensor like this. This part is pushed, and deformation is measured by some technology, and we can measure the force. Then such kind of residual stress is very low. So that will realize a good force sensor. Sorry, this time. Sorry, but this is a photograph, and I'd like to show you the positioning of the cell, and finally we can push it in high speed like this. Okay, sorry, it's almost time. And this is a probe. Currently, we succeeded in position resolution is up to 65 nanometer. So this is a deformation rate, and this is a reaction force. This is quite precise. And we succeeded in continuous loading of, this is a microparticle, but we will apply this technology to the cell. Okay, thank you very much. Then, I think summary of this on-chip robotics. Thank you.
Okay, so good afternoon. My name is Masaru Takeuchi from Nagoya University, Japan. And this slide shows the concept of our research. So in our research, we want to make the 3D cell structures in vitro. And we use the cell spheroids. It's a kind of the cell aggregation to construct the 3D structures like this. So in this research, we use the probe device to handle the cell spheroid and making the 2D patterning of cell spheroid and also the 3D assembly of them. And then after that, we culture them together to get the large cell structures. And such structures can be used for tissue engineering applications like the drug screening or cell characterization. And in this presentation, we especially focus on 3 topics. First one is we need to assemble the spheroid 2D patterning and also the 3D structures. And also we need to check the cell viability after manipulation. And after construct the 3D structures, we need to culture the cells and get the large one structures. So to manipulate the spheroid, we use the probe device we developed. This probe has a micro heater as a probe tip. So we can generate the heat as a probe tip. So, and when we use this probe inside the thermal explosive polymer solution, we can generate the thermalized gel as a probe tip so that we can handle the micro object using the gel generated as a probe tip like this. Okay, so using this probe, we conducted the manipulation with cell spheroids. So there are some cell spheroids, and we manipulated the spheroid using the probe I developed. So as you can see, we can handle the spheroid one by one to make the 2D structures. So we made such a square shape of the spheroid structures at first. And then also we conducted the 3D manipulation like this. So we can put another spheroid at the top of the 3D structures. And after manipulation, we checked the cell viability. And here's the result. So the cell viability shows more than 90%, even if we handled by the thermal response gel. So we can use such probe device to manipulate the cell with keeping the living conditions. And finally, we check whether the cell can be cultured inside the thermal response gel. So we construct such structures and then culture them so that the cells are grown well, so that they connected to each other. So finally, we got the one large structure as like this. So this structure can be handled by the probe again as like this. So I will explain the details in the interactive session. Thank you.
Okay, good afternoon, everyone. My name is Tao Yue from the Nagoya University. Today, I would like to talk about our construction of the vesicle-like structures based on the fluidic self-assembly method. And this is the whole view of our approach and objective. So finally, we want to achieve the three-dimensional vesicle-like structures. So to achieve such three-dimensional structures, we choose the bottom-up method. So we first develop the two-dimensional building blocks, and we can control the cell concentration and patterns inside. And we involve called the self-assembly method to achieve the three-dimensional structures, and which was presented in the previous conferences. So this time we want to solve the problem, which is we only use the one kind of cell, and in the previous research, and also the material is not degradable. So we will improve in two aspects, which is the structure aspect and also the material aspect. So for the so for the structure aspect, we improve our devices to involve multiple inlets to try to introduce different kind of cells in one channel. So based on this, we achieved such as the alternating structures as shown here, and also which was possible to use for investigate the cell-cell interaction by different kind of cells getting together. And also we achieved the double layer shaped structure, which was used to mimic the real structure, real structures of the blood vessel, which this result will be contribute to functionalize our engineered engineered vascular-like structures. And for the for the material aspect, because the previous we used a kind of material called the PACDA, which is not was not degradable. So it's not fitable to use in the in vivo or in vitro applications. So we involved a very popular biodegradable material, which is called Gelma. And the good thing for this one is also photosensitive. So we can use this material in our previous method, such as on-chip fabrication. We demonstrate that we can fabricate the building block by this material, and we involve the cells. And also, we investigate the degradability of this material, which shows very in a relative long-term culture, and which shows that its potential can be used in our applications. So I will talk more detail in the interactive session. Thank you very much.
All right, good afternoon, everyone. My name is Dana Volkman, and I'm going to be talking to you about magnetic actuation of ultra-compliant microrobotic mechanisms. So to give you some background, we're ultimately interested in exploring locomotion at small scales by designing actuated microrobotic mechanisms to explore how insects run or jump and do all these impressive things. So to create the mechanisms themselves, we're using a microfabrication process developed by my colleague Aaron Garrett, which allows us to create monolithically integrated silicon and elastomer MEMS devices. This has already been used to create the jumping device shown in the lower right corner here. But how should we actuate microrobotic mechanisms like these? Well, in the past, we've used these big, power-hungry, traditional MEMS actuators, or we've cheated a bit and used the highly technical method of tweezers to actuate the jumping mechanism. But that won't help us with exploring running at this scale. So we wanted a fast, simple method to actuate these mechanisms and without actually having to worry about microactuator design. So to that end, we're exploring magnetic actuation. On the left, you can see an example of a fabricated mechanism. The link is silicon with an integrated elastomer hinge feature at the top, highlighted here in blue, and an embedded magnet highlighted in red, which has been press-fit into an elastomer sleeve in the center of the link. And the orientation of the embedded magnet is such that when an external magnetic field is applied in the correct orientation, a moment is generated by the embedded magnet, causing the elastomer hinge to bend. Using this principle, we've fabricated a couple of different mechanisms. The first is this single link mechanism with a single elastomer hinge and a magnet embedded in the center of the link, and the mechanism bends in plane along with the direction of the external magnetic field. And we've also demonstrated out-of-plane motion achieved by oriented the embedded magnet orthogonal to the plane. And finally, to test the limits of the process, fabricated this gripping mechanism, which consists of 14 elastomer hinges and 11 silicon links with the magnet embedded in the center link. And the gripper tips can open and close and do this sort of rolling motion depending on the orientation and gradient of the external field. So we've demonstrated this process, and now we want to use it to explore microscale locomotion. And so we'll be using it to fabricate and test leg designs for a legged microrobot, which we can see that we prototyped here. And if you'd like to hear more about the fabrication process or any of the mechanisms that I discussed here, please come talk to me at the interactive session, and you can see some of the fabricated mechanisms as well. Thank you very much.
Good afternoon, everyone. My name is Hisataka Maruyama. I'm from Nagoya University, Japan. In this talk, I am presenting selective and rapid stereo injection of fluorescent sensor encapsulated in liposome using optical control zeta potential and local mechanical stimulus by optical tweezers. In recent years, in cell property analysis, group cell analysis has been performed. In recent years, single cell analysis becomes very important in case such it's a kind of the infection of influenza virus. It's one of the most important issues in the diseases. In virus infections, after the adhesion of the cell, the virus size is very small, 1 nanometer. An injection of the injection into the cell and through the microtube, the virus genome was released and proliferated inside the nucleus. In this state, the pH and temperature inside the cell becomes dynamically changed. We want to know the change. So we need the microsensor and non-invasive injection method by the small areas. So in this presentation, we propose the selective and rapid injection of the sensor the size 1 micrometer to the cell using the optical zeta control and vibration stimulus. First, manipulation of the microsensor size 1 micrometer by optical tweezers, and then contact the cell surface. So cell surface is negatively charged. So we change the surface, the potential of the liposome from negative to the positive by optical charge control. Then applying the mechanical vibrations, the sensor is injected rapidly and rather than without mechanical stimulus. So we use the photochemical materials to change the cis trans shape by UV and by these illuminations. So we fabricate this type sensor coated by ribosome, and we can control the surface potential of the time is so limited. So this is the sensor, and this is the cell. By UV illumination, the sensor was adhered to the surface of the cell. The success rate of the adhesion is improved from 13% to 71% by optical charge control. Then we apply the vibration stimulus to the cell, the sensor B. After stimulus, the sensor B injected inside cell. The red is the cell membrane and green is the sensor. So we improved the injection rate and the duration is reduced. So please come to.
Hello, my name is Tadayoshi Aoyama from Hiroshima University. I'd like to explain our paper, Real-Time LOC-Based Morphological Cell Analysis System using high-speed vision. Recent progress in microscale techniques has made it possible to analyze cells in lab on chip. One approach for automatic cell analysis is vision-based method. In this research, to overcome the problems in previous vision-based method, we propose a real-time vision-based morphological analysis system for fast-flowing cells in microchannel. This is a proposed system overview and its photo. Our system is composed of a high-speed vision platform, IDP, Express, and a microscope, microfluidic chip, and electric syringe pump. The system can process 512 by 256 pixels at 2000 FPS in real time. This means the system can process 500 cells in 1 second. Next, I'd like to introduce the implemented morphological analysis algorithm. There are 2 steps. First step is cell detection. In this step, firstly, input image is converted into binary image, then a connected component doubling is processed. The process is implemented in hardware logic on FPGA. The step 2 is cell characterization. There are a few processing using software, selection of available cells, normalization of cells, counter extraction of cells, and morphological analysis of cells, and dead saving. Finally, the system derives the size and eccentricity and transparency of cells as morphological parameters. To verify our vision-based system, we conducted an experiment using sea urchin embryos using in a straight microchannel. This video shows a real-time demo video of our vision-based analysis system. And this video shows the slow motion image captured by our high-speed vision. And this graph shows the experimental data in different hours after fertilization. The detail will appear in interactive session. Thanks for your time.
Hi, my name is Nobuyuki Tanaka. Today I'm talking about an application of robot technology to the cell culture system. The target of our study is micro-contact printing, which can be used for cell patterning. First, we make a contact between the cell culture dish and the stamp with ink here. Then we can obtain the micro pattern of ink. Now we utilize cell adhesive as the ink. Therefore, we can obtain the cell pattern on the dish like this. But This method is performed by hand. So therefore, the quality is sometimes very low because of sometimes slipping the stamp and sometimes overloading on the stamping force. So therefore, to cope with such a manual problem, we developed a new system for micro-contact printing, which consists of stamp alignment system and a force controlling system. So this is a cell culture dish, and this is a stamp with micro pattern. This is a movement of system detecting the stamp position here by using a laser displacement sensor. And after adjusting the position correctly, we perform the stamping like this. And okay, using this system, we achieved multiple micro-contact printing. In this case, we performed 3 times multiple micro-contact printing. This is a red and the blue and the red, green, and blue color images. So this is a merged image. We achieved an accuracy of 30 micrometer in position. So it can be applicable not only such a simple pattern, but also complex pattern like this. The detail is an interactive session. We will show you the detail. Thank you.
Good afternoon, everybody. My name is Karim Bilari. Today, I talk about studying rotational and including motions of magnetic chain-like micro-robot. The cardiovascular system could be blocked by vascular occlusion, and this occlusion is characterized by plaques formation along the vessel wall, like shown in this figure. In this work, we propose to use external magnetic field generated by coils to rotate and move a chain of ferromagnetic microspheres for blood vessel cleaning. The goal of this work is to investigate the rotational motions of chain of microspheres, and for this aim, it's necessary to generate a magnetic field in the to generate a uniform magnetic field in the workspace. And for this, we use the system shown in this figure. It's composed by three nested coils arranged such that the magnetic field can be controlled in the center of the workspace. The rotational cycle for a chain of microspheres is shown in this figure. In the beginning, the direction of the magnetic field and the magnetization is the same. And when we change the direction of the magnetic field, we create a torque. This torque acts to align the magnetization and the magnetic field. And with this method, we create the rotational motion of the chain. These two videos shows the experimental results. The first one shows the rotational motion in the free space. And the second one shows the combination of the rotational motions and the displacement motions to include this microfluidic channel. Thank you for attention, and if you are interested by this work, see you later in the interactive session.
Hello, my name is Takahiro Motoyoshi from Osaka University. And today I'd like to talk about development of chemical stimulation system. My research field is single cell analysis. In this field, probe-type devices and microflow devices are often used for analyzing. Probe-type devices such as glass micropipettes have good utilities for single-cell analysis and features free positioning and small sporting chemical solution make local chemical stimulation possible. But it has not been researched well. So there were two problems. Problem one, air pressure is often used for sporting, but it is low response speed. And problem two, the spotted solution diffuses and affects each other. We solved them by following methods. First problem, low response speed. We can solve it using electro-osmotic phenomenon. This phenomenon causes small spotting by electrical force, so it is high response and controllable with computer. And we used fluorescent dyes for observing the solution concentration. Second problem is diffusion of the solution. In order to solve it, we propose dual pipette system. One pipette spots solution and the other pipette circuit. Using this system, we confirmed the diffusion area became small. Then we proposed local chemical stimulation system. This system causes chemical stimulation in the area between two pipettes with computer control, and high-speed, high-responsibility control is possible. This system is a high-speed visual feedback control system. Using the system, we measured and controlled the light intensity of fluorescent dyes. We confirmed that local chemical stimulation and its control are possible with the system. And finally, these are examples of utilization of the system. Not only these examples, we will apply the system several uses. Thanks very much.
Hi, I'm John Klingner, and I'm presenting a stick-slip omnidirectional powertrain for low-cost swarm robotics. I work with Dr. Nicholas Carell at the University of Colorado Boulder. We have developed the Droplets swarm robotics platform shown here with a penny for scale. And one of the main motivating factors for us with this was keeping cost as low as possible. To that end, we turned to vibration motors for locomotion. Previous work using vibration motors for locomotion like this have only implemented it with 2 motors in hardware. By adding a third motor, we're able to move the robot omnidirectionally. The mechanism behind this is that we have 3 legs and 3 vibrating motors opposite each leg. The animation in the top right shows what we call a step, where one vibrating motor is spinning, which causes the robot to pivot about the leg opposite. By taking a sequence of steps, alternating motors, the droplet can walk or move in a straight line, as pictured in the lower right, where by alternating the 2 motors on the bottom of the image, the robot is able to move towards the bottom of the screen. The downside, however, of these low-cost actuators is their performance is fairly inconsistent. To mitigate this, we calibrate the robot. Specifically, we adjust the duration that we turn each motor on for in a step such that the size of each step is the same. This calibration can be done manually. In the paper, we present an automatic calibration method using an overhead camera, and we could also do this with range and bearing feedback from other robots in the field. Yeah. So I have hardware for you, and would be happy to answer any additional questions you have in the interactive session. So thank you for your time.
Good afternoon. I'm Jianguo Zhao from Michigan State University. I will talk about a new control method for nanorobotic manipulations. Recently, atomic force microscope, or AFM, has been widely used to manipulate nanostructures. The fundamental requirement for such nano manipulations is to move the tip position from one point to another point. In applications such as DNA manipulations, it is critical that we can achieve sub-nanometer accuracy. For nanoscale motion control, most methods based on feedback from position sensors, but sensors can only be added to piezo actuators instead of actual tip. Meanwhile, sensor noise at nanoscale prevents the sensor from providing accurate sensor feedback. To address these issues, we propose to use local scan image for feedback. So give a desired and an initial local scan image. The tip position can be guided to the desired location with visual serving algorithms. However, most visual serving methods formulate the problem in vector space. There are two potential issues for these vector space approaches. First of all, they need to extract features and track features during the serving process, which is difficult at nanoscale. Second, they need calibration for coordinate transformation, which is also difficult at nanoscale. To solve these problems, we propose a new non-vector space control method, which considers the image as sets and formulate problem in the space of sets, or long vector space. Based on such a formulation, we can design a controller to control a tip to a desired location. In this case, we don't need any calibration or feature extraction. To deal with the image noise problem, we integrate the Kalman filtering and non-vector space control to design stochastic controllers, and we proved the stability of the system. We performed some experimental results using AFM systems. Given the initial and goal image in the left figure, we can obtain the results shown in the right figure. Both the task space error for both normal and stochastic controllers can be seen in the figure. From the figure, we can see that both controllers are stable, and the stochastic controller has a small steady-state error, which is about 1.5 nanometer. I will talk about detail in the interactive sessions.
Hello, my name is Minas Liarokapis, and I'm here to present a paper on task-specific robust grasping for multi-figure robot hands, done in collaboration with George Boutselis, Charalambos Pethiolis, and Kostas Kyriakopoulos from National Technical University of Athens. The motivation behind this work is the fact that humans execute tasks in a task-specific way and rely on information derived from their skin in order to grasp or manipulate everyday life objects. We have to derive task-specific stable grasp, so we have to conclude the task-specific grasp configuration and minimize contact forces to robustly perform the desired task. To do so, we introduce the concept of Q-distance proposed initially by Zhu et al. The object has to be grasped by a mechanical robot hand, which has joint torque constraints, needs a configuration capable of exerting grasping forces with low joint torque effort. We have contact points uncertainties and object properties inaccuracies. So, can we guarantee force closure? And can we do so despite the inaccuracies and the uncertainties? We employ tactile sensors in order to relax the uncertainties and the magnitude of uncertainties, for example, contact points deviation. The force sensors are ultra thin, measure the pressure magnitude based with sensors based on piezoresistive technology, and can be used to compute also the contact centroids. So the outline, at first we compute offline and task-specific robust configuration. Then the robot moves towards the desired configuration, the closing phase. Robot figures stop moving when contact is detected by the tactile sensors, closing and contact detection phase. Then we obtain the joint positions from the encoders, the contact centroids from tactile sensors. We compute the position of the contact points, solving the forward kinematics, and we determine sufficient contact forces to grasp the object. Let's see a video of the experimental validation. Here you can see the initialization, the reach to grasp phase, where the robot arm moves in an anthropomorphic manner to grasp the object. The robot hand starts closing its fingers. We detect contact with the tactile sensors. Each finger stops moving upon contact. We exert the desired forces, and then we execute the task to rotate an object full with liquid. Regarding future directions, we plan to extend our methodology considering objects with complex geometries that cannot be described by analytic equations. And instead of applying contact forces with joint angle displacements, we plan to implement advanced force control schemes. Thank you very much.
Hi, my name is Jun Hyung Ha from Seoul National University, and the work I'm presenting is joint with Frank Park of Seoul National University and Pierre Dupont of Harvard Medical School. This paper proposes a way to achieve elastic stability in concentric tube robots by determining the optimal tube pre-curvature. Concentric tube robot is a type of continuum robot designed for surgical applications. As shown in the figure, it is comprised of nested combination of pre-curved superelastic tubes and manipulated by rotating and translating the base of the tubes. As you can see in the video, the robot can exhibit certain snapping behavior. As the base is gradually rotated, the tube stored elastic potential energy, which can then suddenly be released through a rapid untwisting motion. There has been several previous studies on this instability problem. In previous work by Dupont, a mathematical condition was derived for stability of tube pairs with constant pre-curvature. According to this condition, a nitinol tube pair should have a tip orientation angle less than 79 degrees in order to be stable. For practical reasons, we want to increase this value up to 90 degrees. One way to overcome this instability is to consider tubes of non-constant or varying pre-curvature. One of our main results in an analytic, is an analytic condition for stability of tube pairs of non-constant pre-curvature. We find that local torsional behavior around the straight configuration, in fact, determines the stability of the tube pair. And we obtain an analytic stability condition from this local behavior. Using this condition, we formulated an optimal design problem in which the goal is to determine the optimal pre-curvature function that maximizes tube pair stability. We, we devised a numerical algorithm to determine this optimal pre-curvature function and find that by using a non-constant pre-curvature function, the tip orientation angle can be increased to more than 90 degrees while still maintaining stability. Please come by if you would like to learn more details about our work. Thank you.
Good afternoon, everyone. My name is Prashant Kumar. I'm going to talk to you about cable stiffened flexible link manipulator. Flexible link manipulators have been introduced as a means of increasing the manipulation speed, reduce energy and power consumption, and consequently the size of the motors used. The advantages of flexible link manipulators mainly come from lightweight or low inertia. This is also a disadvantage because of the flexibility. There's a problem of tip vibration. Various control techniques have been proposed in the past to overcome these problems. However, industry adaptation of FLMs is poor due to various reasons. One of them is complex control algorithms required for reducing tip deflection. In this paper, we propose a change in design of the manipulator such that it retains the advantages of low inertia and at the same time allows conventional control algorithms to be used. In short, we try to increase the bending stiffness using axial stiffness of cables connected between the tip of the manipulator and a rigid hub. This is the basic working principle. Here we derive the relationship between the bending stiffness and axial stiffness. Here the relationship is squared by 4L square, where h is the thickness of the link, which is very small, and length is L. We see that the axial stiffness is quite large compared to the bending stiffness, and if we are going to use the axial stiffness for reducing the tip deflection, we can use very small cross-section and very small mass. An example of this idea can be found in cable suspended bridges. So ideally, we would like to support the flexible link manipulator using two supports on either side using strings. However, because of this, the moment of inertia is going to be quite high. So practical ways of introducing the strings is to attach the string at the tip and the rigid hub. So this is a video of a experimental result. Here the manipulator moves at 45 degrees rotation in 0.5 seconds, and because of the high accelerations of the payload, there is a radial force introduced which will cause buckling-like oscillations. These buckling-like oscillations are not found at lower accelerations and speeds. So to summarize, the tip vibration problem can be efficiently addressed using cable stiffening, and at higher accelerations, buckling-like oscillations are found, and we see that there's a possibility of avoiding these buckling-like oscillations by adding additional strings along the length of the flexible link and connected to the rigid hub. Thank you very much.
Hello, my name is Sung-Kyun Kim from Carnegie Mellon University, and I'll talk about robotic handwriting multi-contact manipulation based on reactional internal contact hypothesis. So let's start with a short video. My robot, my daughter is drawing some alphabets on the book, and you can find that we have multiple contact points with the object when we do handwriting. So what do we grab that object like that? Because the multi-contact manipulation can provide powerful grasping of the tool body and dexterous manipulation of the tooltip at the same time. But it's difficult for robots because there's not many actuators and sensors available for the internal contacts. So this is my key idea. Just use the internal contact force as a reaction force. So if we want to draw a line to the right, then we need to generate the force and moment as shown in the figure as a blue arrows. And at that setting, if we use the internal contact force as shown in the red arrow, we can significantly reduce the finger forces that should be actuated by the robot hand. So using this hypothesis, we can drive the formula for reduced desired range for finger forces. And we should note that there's some directional condition to get the actual reduction effect. So based on our reactional internal contact hypothesis, we can develop force manipulability for multiple robots to find the optimal grasp configuration. So I mean how we should grasp the pen. And we can apply it to the grasping force optimization problem to compute the optimal finger force. So this is the simulation results. By applying our method, we can do the exact drawing using our method, but significantly small finger forces that should be actuated. And you can find out that there are some cases we can actual reduction effect according to the direction condition. So that's it. Please come and see to figure out what is more in detail. Thank you.
Hi everybody, my name is Ivana Palunko and I come from University of Zagreb. And today I'll be presenting work done together with my colleagues from Technical University of Munich on cooperative suspended object manipulation using reinforcement learning and energy-based control. So cooperative dynamic object manipulation can extend the manipulation capabilities of robot-robot and human-robot teams, which can be applied from automotive industry to elderly care. So if we consider flexible object manipulation, we can decompose it in two actions, a rigid body swing and a suspended object swing. In this work, we focus on suspended object manipulation. So our goal is to enable the robot to manipulate objects of variable shape and size cooperatively or unassisted without retuning the controller. So basically, the bottom line is we want the suspended object to reach a desired energy level, which can be then mapped to a desired maximum deflection angle. So how do we do this? Is if we use a robot as a manipulator, the control input is the acceleration of the robot end effector, and the feedback from the state is obtained through a robot's torque sensor from the end effector as well. So one way to do this is through energy-based control input, where we shape the acceleration with a sign where A specifies the direction and the amount of energy flow. With A being positive, we are injecting the energy, and with A being negative, we are decreasing the energy in the system, and A omega times the energy flow. But both of these parameters are dependent on the model, so they vary with respect to the shape and size of the object. So what we want to do is to adapt to it online. So we are using the least square pulse iteration algorithm, which is an online reinforcement learning-based algorithm, which gives us suboptimal parameters with which we inject the energy into the system or decrease it. The proposed algorithm is verified experimentally, and if you want to see more details or hear about it, visit us at our interaction booth. Thank you very much.
Okay, ladies and gentlemen, welcome. My name is Tobias Timmerding, and I'm from the University of Oldenburg, and I would like to present a robotic dual probe setup and handling strategy to perform reliable pick-and-place processing on a nanoscale. So if you think about doing manipulation on a nanoscale, exemplarily here, handling of nanoscopic particles, it's often not reproducible. Especially if you think about the release of particles, it's complicated and time-consuming, as you can see here in the two examples. If you use a tip for picking a sphere, that is simple possible, but then maybe the particle will remain on this tip and cannot be released. The same is true if you use a jaw gripper. For example, here, the sphere can be kept on one of the jaws. So we developed a dual probe setup, which is purposefully utilizing the parastatic adhesive forces, which are always represented on a nanoscale. At first, we developed a nano-robotic setup, which is located inside an SEM and consists of multiple nano-positioning stages for coarse positioning and fine positioning. And here, in yellow, you see the anti-factors. So how do the anti-factors look like? At first, we have a high aspect ratio tungsten tip and a piezo-resistive cantilever with a so-called adhesion pocket. Our handling strategy looks as follows. At first, the gripper moves down towards the substrate and the particle. So the particle is located inside the adhesion pocket, and we can move the adhesion pocket up from the substrate. Then we move our gripper towards the sharpened tip, below it, move the sphere in contact with the tip, and then, for example, we could exchange the substrate to a building upside. Then the substrate is moved up, and our tip is moved down. So now we have used parastatic forces, and the forces are here stronger between the sphere and the substrate, so the sphere will remain there when we remove our anti-factors. Overall, we were able to use these kind of handling strategy to assemble special tailored 3D photonic crystals like these pyramids you can see here above, or for example, photonic heterostructures consisting of spheres with different kind of diameters and different kind of materials like melamine or silicon. And also we were able to create photonic crystals with targeted designer defects where, for example, some spaces are left open, which is here targeted. And overall, this handling strategy and this especially the reliability allows us for automation in the future, which is one of our main tasks and which I can tell you in the interactive session in the next few minutes. Bye.
Hello, my name is Tim Caldwell. I did this work with Dave Coleman and Nicholas Carell at the University of Colorado. So I'm going to talk about robotic manipulation for identification of flexible objects. So the question I want to pursue is, can Baxter, which is the robot shown here, can it identify parameters of this rubber tube just by manipulation alone? So no vision, just the contact. So the main challenges are, first we need to come up with a model and a simulation. So in order to model the flexible object, we approximate it with a spring mass model, which is often done. And the advantage here is that the model of the arm and the model of the flexible object are handled in the same way. And we do that using variational integrators. The advantage of variational integrators, if you're familiar with them, is that they have nice energy behavior. And the main contribution of this paper is gradient calculation, because we want to do an iterative approach, an iterative optimization approach to identify the parameters. The gradient calculation that I come up with is in the context of the variational integrators. That's the main contribution. So for this model, we approximate the flexible object with 12 links. The joint between each link is a spherical, joint, and we can get nice phenomena like twisting and bending of the object. And also we can get a very realistic looking simulation of Baxter manipulating the object. So in order to do the identification, I use steepest descent, and of course, we should expect steepest descent will give us linear convergence, which we find out that it does. And also shown on the right is just showing the identification for the different iterations of the optimization, showing that it's converging to the measured end effector trajectory. And the optimal solution ends up comparing the actual run and the simulation. They end up looking fairly similar. And for future work, we want to look at more complicated geometries, such as this Y shape shown here, and then also one arm and two arm measurements and manipulation. And we've noticed, playing around with this, that we get an interesting identifiability issue, which I'd be happy to talk about. So come by. Thank you.
Hi, my name is Jacob Rosen. I'm with UCLA and my colleagues at UCSC. We study the redundancy of the human arm, or more officially, joint coordination in reach and grasp movement. So why do we study this? So for example, if I want to grab this object, I need to know 6 numbers, X, Y, Z, and 3 angles around these 3 orthogonal directions. And if I have a robotic arm with 6 degrees of freedom, I can grasp this object with at least one configuration. However, the human arm has 7 degrees of freedom. So once I grasp this, I can move my elbow like that. And this is an expression of the human arm redundancy. The question is why the brain pick one configuration of the arm over essentially endless configurations. One way to resolve this problem is by recording data from people who are reaching and pointing to different locations. And instead of looking at the 7 degrees of freedom, we are of the 7 joints of the human arm, we are breaking down them into wrist position and wrist orientation and the swivel angle, which is the angle that represents this position of the elbow. The reason why we are interested in all of these is because we are studying exoskeletons. And this is the system that we are studying. It's a system with 7 degrees of freedom. And so he's actually demonstrating all the different degrees of freedom of that system. And obviously, we want to resolve the redundancy, and I'll demonstrate you how the redundancy is shown with the Excel. So what he's doing is the end effector is fixed in space, and then the elbow can do this endless configuration. The question is how the brain would pick the configuration of the arm to grasp a specific object in space. And if you want to know how the brain does that, then I can tell you about that later. Thank you.
All right, hello everyone. My name is Adam McMullen. I'm an undergraduate student at Rice University, and today I'm here to talk about a robot system design for low-cost multi-robot manipulation. So our goal is to use large numbers of robots to manipulate large objects, and we specifically design a robot system and manipulator that can support distributed algorithms for multi-robot manipulation. In this paper, we detail the key hardware designs of the robot and the manipulator. So some motivation. Ants are able to manipulate objects with limited sensing. They're able to collectively reach a consensus on where they're going and get their food where they want to go. Kiva Systems has developed a fascinating hardware distribution robot system where they have lots of robots that are controlled by a central controller. At Harvard, the Termes project demonstrated how simple robots can use distributed algorithms to build simple construction projects. And one can imagine one day a future where we send swarms of robots to earthquake rubble to search for survivors. So the opportunities for multi-robot systems abound. The R1 robot was developed specifically for research focus. Namely, we wanted to keep it simple and cost-effective. And the kit cost of this robot is around $250. This means we can make like hundreds of these robots very, very easily and do large tests with them. The mechanical design is also very simple. It consists of 2 circuit boards, a top board and bottom board, and 3 custom plastic parts: the chassis, the bump skirt, and the bump skirt springs. It only requires about 14 screws to assemble. So this design is very simple and very easy to make. The R1 has a very rich sensor suite, and it has some very nice specifications as well. But some of the sensors I want to highlight are the light sensors, the gyroscope, accelerometer, the infrared transmitters and receivers, which allow the robots to communicate, localize themselves, and detect obstacles, and the quadrature and coded wheels, which provide high-resolution velocity feedback. Further, I want to focus on the injection-molded bump skirt, which provides 8-bit directional contact feedback. This bump skirt is very important for our manipulator, which attaches directly to the robot. Essentially, you have a top gripper paddle and a bottom paddle, and they sandwich the R1. These 2 paddles are actuated by a servo, which allows them to open and close, and attach to vertical features of objects. The most important part of this design is that it was intended to act as a pin joint. Namely, the whole design is free to rotate around the entire object. This means the robots cannot apply a net torque to anything they touch, but only a net force, and it greatly simplifies the algorithms we wish to explore. Here are some videos which demonstrate via RC control what we intend to do with these robots. Right now, we are currently developing the algorithms, but this just shows what we intend to do. And I hope you guys will come by to the interactive session and ask me more questions if you have them. Thank you very much.
Hello everyone, I'm Sven Schneider from the Bonn-Rhein-Sieg University, and I'm going to present you our paper, The Declarative Specification of Task-Based Grasping with Constraint Validation. So first of all, let's have a look into the ingredients of a robotic grasp. So first of all, there is of course the object which is going to be grasped. Then we need to consider the task which we want to achieve with the object after grasping, and also the hand, so basically knowledge about the robot which is performing the grasp, and later on also the task. All these domains are independent of each other, and we look into describing them in our grasp domain definition language, or GDDL for short. And it captures the knowledge within these heterogeneous domains. So as an example, I would show you how we, for example, represent an object in GDDL. So on the right-hand side, you can see a spray bottle. And on the left bottom, you can see how this textual representation looks like. So for example, it's important to capture for articulated objects the kinematics. Like for example, in the spray bottle, we have the trigger which we can activate, or also the cap which we can screw or unscrew from this bottle. Then another important issue which we need to represent is different regions of the object. So for example, if we have this, this nozzle and the area in front of it, so basically the spray cone, this is something which the robot also needs to consider during grasping. For example, during spraying, it should not put the hand into this region. Then we also consider the affordances of the objects, and also frames and transformations. Like for example, you can see we have the body of the spray bottle in the right bottom, and also the cone frame attached to the nozzle. And this is all captured here in this textual description. For other domains, we also have investigated this, so as outlined before. And the results are that basically we can, by this explicit description of the different domains, first of all, increase reusability, because we can, for example, easily switch the hand which is performing the task with a specific object, or also the other domains, and also due to constraints which we formulate, we can increase the robustness of our system. If you want to know more, then please visit my booth. Thank you.